Hello, everyone, and welcome back. We are moving on into Chapter 5, where last lesson in 5.4.1, we learned about applying the chain rule with the fundamental theorem of calculus. Now, this last part of Chapter 5, 5.5, it's a two-part lesson, which we're doing in one day, 5.5.1 and 5.5.2, where we're going to learn an additional skill, kind of different than 5.4, where we're talking about indeterminate forms and taking limits of those. Now let's recall how to evaluate limits first. So recall, evaluating limits before I get into this new topic. So say, for example, you had the problem, the limit as x approaches 1 of x squared. Now we can do that simply by just plugging in 1. And if you plug in 1, we would get that the answer is 1. Now, we could also determine this graphically, of course, and that is, a nice way to see this, where if I graph y equals x squared, a sketch of it would look something like this, where if we're evaluating out 1, and we know that it's at 1, 1, this point, we would say that the limit as x is approaching 1 from the left of x squared, from the right, is equal to 1. We would say that the limit as x approaches 1 from the left of x squared, so from the left, it's also approaching 1. And since these are the same, well, that implies that the limit as x approaches 1 is equal to 1, which, of course, is the same thing we got by just plugging it in. But that is a graphical approach. So that was evaluating limits, both algebraically and with a graph. Now, what if I gave you another problem to recall this? So let's say I said, what's the limit as x approaches 2, this time of a fraction, x plus 2 over 2? Okay. Nothing changes here because, again, we could just plug in 2 and you would get that's going to equal 2 plus 2 over, well, I'm not going to put it over 2. Let's put it over x. All right. But it doesn't change much. It's going to be, if you plug in 2, it's going to be 2 plus 2 over 2, which gives us 4 over 2, which is equal to 2. And we get our answer. And if we wanted to see the answer graphically again, if we wanted to check graphically, I actually don't know what this looks like, so let's bring out my calculator and look. Right, so if I was to put that equation in on my calculator, x plus 2 divided by x, and we look at the graph, I can see it looks something like this, where you know that at 0 there's an asymptote, so it's something like this. And if I was to, calculate the value at 2, I would see here that it actually is at 2. So the graph is looking something, like this. That's a very poor little note. Poorly drawn, Mr. Hine. What is wrong with that? That clearly doesn't look like my calculator. But the point being that we can see from this graph that as you approach from the right, it equals 2. As you approach from the left, it equals 2. Therefore, the limit as x approaches 2 of that function has to equal 2, since as it approaches from the right and left, they are equivalent. And that's great. So that's what we have been doing. Now, how does it apply to what we're doing now in determinate form? So what if I gave you a different type of limit? What if I said, what's the limit as x approaches 0 of sine of x over x? All right, a third problem. Now, if we try to just evaluate and by plugging it in or substituting, if we try substituting, what's going to happen? No, my lead. Put that back in. Okay. You're going to get sine of 0 over 0. And sine of 0, I'm talking about the y, the vertical distance, at 0 on a unit circle, which is on the far right. So that's 0. And we get 0 over 0, which we can't do because we can't divide by 0. So it's like, what do you say, undefined? Is it like, that's strange to us? And this is an example of this right here, or this whole thing, I wouldn't just circle that, this whole thing is an example of a limit of an indeterminate form. Where an indeterminate form, so indeterminate forms are anything where after you evaluate you get 0 over 0, or you get infinity over infinity, or 0 over infinity, or infinity over 0, etc. There's a few more in the book, but these two right here, these are the most common, especially in our class for AP Calc AB. But the idea is if you ever come across a problem where when you're trying to evaluate a limit by just substituting and you get one of these forms, well, that's called an indeterminate form. So we need a method for calculating this, right? Now, this lesson, we're building up to it. So how do we do this? All right. So we write that down. What do we do to solve this? All right. So one approach you can do, if I scoot this down, method 1, and this is problem 148. What did I write down? 148, which you don't have to do, but the problem that I did assign 150 and 151, they're going to ask about questions from 148 and 149. So in 148, there's one method we could do where we can use the graphical approach that we know how to do with limits, where you evaluate it from the right and from the left. And if they're the same, then we can say that the limit exists. Even though the function doesn't exist there, which then means it's not continuous, but we can still say the limit exists. Now I'll write that all down because I did say a lot there, so you are still with me. So method 1, let's look at it graphically. So we're going to do, in our calculator, sine of x over x. And we want to see what's the limit as x approaches 0 here. Okay. I'll bring over my calculator. And let's look at this. So let's do sine of x divided by x. Hit graph. You can see it looks something like that. I'm going to zoom in to get a better idea here. Okay. And I can see that the graph looks something like, this. Where what is that value? Where if I just, use my arrows, I can see that, the y value is somewhere around, at 0, it's getting close to 1. And if I tried to calculate the value at 0, notice when I try to calculate at 0, I get nothing. It's an error because, again, we can't do 0 divided by 0. So we can see it looks something like this graphically, where this is at 1. And if you wanted to use a calculator for that, you could do second calculate a value. And you can't do 1, but you could do like 0.99999, very close to it. And you see that it's, we're valuing it at 0. I was going to say that's really close to 1, and that's not what I was expecting. I was expecting 1. Mistype that. Calculate the value of point 0.00000001, or you can do negative because we're valuing it close to 0, and you see that it's at 1. But anyway, graphically, my main point being is as you approach, as x approaches 1 from the left of sine of x over x, it's equal to 1. As x approaches 1 from the right, I guess I shouldn't use as, I'll actually write it properly. The limit as x approaches 1 from the left, the limit as x approaches 1 from the right, it's going to equal 1. But at 1, it's actually an open circle. So sine of x over x equals 1. So therefore, we could say that this answer, the limit as x approaches 0 of this indeterminate form, is equal to 1. And there we go, since they're both the same. Now do note, side note, that this function, sine of x over x, is not continuous at x equals 1. Well, it's not continuous at all. You're not really continuous at a specific point. You're not continuous because remember that there's the 3 conditions, but that condition where sine of 0 over 0, aka f of 0, does not exist. All right. The limit exists, and that's great. The limit exists, but that's only one condition. Remember, there's three conditions. The limit has to exist, the function has to exist, and these two have to equal. But in this case, the function doesn't exist at that point. So a little review on continuity. But that is one approach you could take, is using graphically, look at the limit from the left and right. And if they're equal, we know the answer. Now, what's a second method we can do? And I need another piece of paper for that. And that was problem 149. So if I try to leave that up there. All right. Method number 2 is problem 149. And this is a unique method, and this is going to build into what you're going to see in the next lesson. So this was the problem. And the idea, and we're observing something here, is what if we look at the rate at which the numerator, the rate, not at which, the rate of the numerator, as x approaches 0, and then we'll compare that to the rate of the denominator as x approaches 0. Okay. So let's look at a graph of this. So we're going to graph this, but we're going to graph sine of x, and then we're going to graph x. So two different functions. And I'm going to graph it on a scale of 0 to 0.5, 0 to 0.5 per the instructions of the problem. So let's see what this looks like. So I'm going to graph just the numerator, sine of x, just the denominator, x. Look at it on the window from 0 to 0.5, 0 to 0.5. If I do that, what do I get? Well, that first function is sine of x. So that's sine of x. And this next function, you don't even see it, is x. And notice that they look almost identical. They look something like this, where there's sine of x and there's x, right? The rate at which they're approaching 0, well, these two are identical. So what that tells us is that if they're identical, then the ratio of the two, the ratio of sine of x over x, will have to equal 1 if they're identical. And notice, and it's just an observation, that this is the same thing we got with method 1, which is 1. So what's the observation here? What's the connection that we just made? So a possible connection, as this leads into the next video, possible connection from that observation is that for indeterminate forms, so if for the limit as x approaches some value h of f of x over g of x, where h is a, it actually can be any positive number, so h is a real number. All right, that just means any positive number, or any negative number, it's any number, even decimals. So for the limit as x approaches h of f of x over g of x, where h is any number, if f of x over g of x is an indeterminate form, for the limit as x approaches h, such as 0 over 0, infinity over infinity, 0 over infinity, infinity over 0. All right. In other words, if you can't calculate it by substituting, so I'll just even put that, in other words, if you can't calculate the limit by substituting, then dot, 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 I don't even know if you saw that. What did we determine with this method 2 equaling method 1? Well, what we're thinking then is that the limit as x approaches h of f of x over g of x can be found by doing the limit as x approaches h of the rate of f of x as x approaches h over the rate of g of x as x approaches h, which, what's another way of saying rate of f of x or rate of g of x? That's the same thing as saying the limit as x approaches h of f prime of x. Remember that derivatives are your rate over the limit as x approaches h of g prime of x. And I actually messed up here. There's no limit there. The idea is if you just look at the ratio of the rate of f of x as approaches h, the rate of g of x as x approaches h, which we can write that as just saying the limit of the derivative. And that's the idea there. But we don't know that for sure. That's just a possible connection. But that actually is a thing, and you're going to learn the name of it in the next lesson. But for this lesson, you have your two methods. We talked about one indeterminate form is where the two methods are method one, graphically, very nice method, probably the easiest method, and method two, which is looking at the rates of the limit, rates of each function as that limit approaches whatever value you're looking at. But that observation is key to what you're going to see in the next video. All right. Hope that made sense a little bit. If not, definitely come to office hours or ask. All right. Bye-bye.